from across the globe, from the centre of aerospace. And now to you.
Thank you for downloading the Aero Society podcast from the Royal Aeronautical Society.
Thank you very much indeed. And my own little bit of housekeeping, I've scattered some postcards of this wonderful aeroplane around the tables. Help yourself, take them home. If there's none on your table, steal them from somebody else's table. And I also brought some leaflets about various aspects of what we do over there. Again, please help yourself later on. Makes me really happy if I take a lightweight bag home with me. So, good evening. Thank you very much for the invitation to come and talk. I'm going to be talking about flying for atmospheric science, and for an awful lot of people that's all about an aeroplane called Snoopy, but hopefully I will be able to show you that it's an awful lot more than that. But I'm going to go back a lot earlier, first of all. You'll probably be aware of a man called Charles Darwin and the voyage of the Beagle. The Beagle was captained by a gentleman called Robert Fitzroy, who was a very scientifically minded ship's captain in the middle of the 19th century. When that was all over and Darwin went off and wrote a book that a few people noticed, Fitzroy carried on in his own scientific directions. And he made a bit of a laughing stock of himself by saying several times in public that if we had good enough science and if we had good enough observations of what the weather was doing in the morning, then we might be able to predict what the weather would do in the afternoon, which nobody really believed. But he kept on about it, and in 1854, he managed to get formed something called the Meteorological Office of the Board of Trade. And the Meteorological Office had a primary job, and it was to predict storms at sea. And that was basically the origin of the shipping forecast. They got quite good at that, and certainly Britain as a maritime nation really appreciated not losing too many ships, so that went down very well. By 1861, they'd got to the point where they were publishing weather forecasts in the morning newspapers. And that carried on through the 19th century, and they were steadily improving the science, and the Meteorological Office was getting quite good at what they did. And then in 1914, a war kicked off, and the Meteorological Office, which by this point was part of the Admiralty, went along to the War Office and said, "You seem to be about to start a major war, and strikes us that it'd be quite handy to know what the weather condition's going to be like in your various theatres. Can we help?" And allegedly, some general of the sort that we specialised in 1914 said, "The British Army fights wars with cannon and bayonets and not with weather forecasts," which made perfect sense as a viewpoint until somebody invented poison gas. At which point, a few hours' warning of which direction the wind would be blowing from was a really useful piece of information. So this got the general's attention, and by 1917, 1918, right across the Allied forces, every theatre commander had access to weather forecasting information, and tens of thousands of weather balloons were being launched every month to support that. And in parallel with that, of course, the aeroplane, which had been a bit of a peculiarity in 1913, by 1917 was a major weapon of war. So a few scientists, particularly a fellow called Dobson, who'd been mucking around with some experiments from Central Flying School in 1916, a few others, managed to pull together what became known as the Royal Flying Corps Meteor Flight. in a tradition that I have to say we continue to this day. They were issued with a load of obsolete aeroplanes and told to do their best with it. In this case, these are Armstrong Whitworth FK8s, but they were fitted with recording instruments, they were fitted with cameras, and they were established at a place called Berck-sur-Mer in France, and from March 1918, they were flying in support of weather forecasting, in support of the science, and they did a few quite clever additional things, like, for example, they were the first people ever to take photographs of cloud tops, which, from the point of view of scientists studying weather in 1918, was a really radical thing, because most of these people had never seen the top of a cloud before. And as you can see, it was a very modern organisation. It had a proper logo and everything. And this carried on through to the middle of 1919, when, in the way of most of the Allied forces in 1919, they were disbanded as we slipped very happily into peace, and we really wanted to stop spending quite so much money. However, realised very quickly that certainly we still needed weather forecasting for all good reasons, and we still needed aircraft in support of that. So 1924, a successor was formed, which was called the Met Flight, and that was based at Duxford. And again, continuing the tradition of obsolete aeroplanes, they were issued with Siskin 3As. And they were still operating those aeroplanes in 1939, and I'm not sure they were even modern in 1924. And they were flying twice a day, every day, doing Met observations, climbing up through cloud on very primitive blind flying panels, and doing a lot to support weather forecasting. A whole bunch of people were there, some really very brave men, because they were flying in extremely dubious conditions in some very basic aeroplanes. One in particular is worth a mention. The commanding officer for about a year and a half was a gentleman called Geoffrey Quill, an RAF flying officer, who then left, and you might have heard of what he did next. He went off to go and be deputy chief pilot at Supermarine, and ended up being the test pilot most associated with the Spitfire. The other, and he did get an Air Force Cross for the work he did as CO of the Met Flight. The other thing that I think is worthy of mention from the Met Flight days was that they developed a lot of the techniques of positioning aircraft according to weather, simple things like having a telephone network of phoning around observers at different airfields saying what's going on there to position aircraft. And I tend to think a lot of that work naturally flowed into the way we managed, for example, the Battle of Britain. 1939, the Met Flight was disbanded, not because the work was no longer required, but because you weren't going to do it with a handful of obsolete biplanes from one airfield. So early on in World War II, every air wing had a Met Flight. They were simply using whatever aeroplanes were available, whatever pilots were available, but they were doing a lot of work to take Met observations and feed the developing and very, very important weather forecasts. Now that, if I can bring in a little bit of terminology, is what we would call now Met reconnaissance flying. And that is about measuring conditions now to feed into the forecast you are creating now. That is quite different to Met research flying, which is about understanding the deeper physical processes and improving the whole science of forecasting and your whole understanding of the atmosphere. And in fact, my opinion, they really lost out in the Met Flight because they really didn't engage with developing science. And given they were right next to Cambridge University, why on earth they didn't, I don't think we'll ever know. But in 1942, it was realized that there was this gap. And a fellow called Alan Brewer, he was a Met Office scientist with an MSc from City University, was told, go to Boscombe Down, and we're giving you some aeroplanes and a sergeant, and we would like you to form a high-altitude flight. And here is the problem, Dr. Brewer, he became Dr. Brewer later, we'd like you to solve, and it's contrails. Because when you're flying high-altitude bombers over Germany, contrails are a little bit of a headache. They do tend to advertise your location. So he was given this problem, work out why contrails are happening and work out how to avoid them. So he started off, with, of all things, a Flying Fortress and a couple of Spitfires, all of which were pretty fundamentally useless as research aircraft. They rapidly switched over to Hudson, Bostons, and what became the favorite aeroplane for research, the Mosquito. The Mosquito was brilliant because it was high performance, it had a really high ceiling, it was made of wood, so it was really easy to cut holes in it and stick instruments in, and you had a spare seat so you could fly with a pilot and a scientist. Dobson, who'd done the 1916 experiments at CFS, got hauled out of retirement and sent to work with him. And between them, they first of all started solving fundamental problems of instrumentation, because they realized before they were going to get anywhere, they needed to do things as simple as measure temperature in cloud, water content, balance of phases of water, and so on. And they ended up doing quite a lot of basic science and then feeding through into solving the bigger problems that they were then sent to solve. I don't think they really ever solved the contrail problem. And interesting, I managed to get a conversation a couple of years ago, not with somebody from that era, but with an American U-2 spy plane pilot. And I said, so in the 1960s, you're flying over Russia, you really don't want to draw attention to yourself. How did you avoid contrails? And he said, oh, it's very easy. We just had a rear view mirror, look behind the aeroplane, and if we had a contrail, we changed height until it stopped. Which I suspect is probably what they were doing in the bombers over Germany as well, but I haven't found any record of that. 46, the war ended, but the work didn't. So they disbanded high-altitude flight for all of about 3 months and then reformed it with the same people, the same aeroplanes at Farnborough, and that became known as the Met Research Flight. And the Met Research Flight was founded on a model of 3 aircraft types at any time. And it was typically a high-performance aeroplane, such as the Mosquito, briefly a Vampire, and then became the Canberra, of a cheap hack, which for a lot of its history was the Varsity, and then with a big aeroplane that you could put a lot of instruments and run really big experiments. And in the early days, that was the Halifax, and it later became the Hastings. The work they did was fantastic. Really high quality science, really made a difference, really pushed forward the boundaries of understanding of the weather. I'm going to just mention one specific piece of science because I think it is the single most important bit of science they did in that whole period from 46 to 2001. And the science they did was to track dust and radioisotopes released into the stratosphere. And what they basically showed was if you set off a nuclear weapon and it will throw up fallout into the stratosphere, and within about 48 hours, that's going to cover most of the planet. Or in other words, nuke Moscow and New York gets it within the week. The Americans picked up on that. They then went just threw a bigger budget at it and repeated the experiment in the US and came up with exactly the same conclusions. And a whole bunch of scientists made quite sure that those reports were on every world leader's desks, and I think it may well have prevented World War III. So that carried on. They weren't the only people in the game, but they were the main research body. I'd like to mention two other major players in the game. One was FAAM, Temperature and Humidity Flight. They operated photographic reconnaissance Spitfires out of, it was either Speke or the other Liverpool airfield, I've suddenly forgotten. Liverpool anyway. And they were flying high altitude flights several times a day, very much in the model of the Met flight pre-war, using those Spitfires. And they were doing that up until the 60s. And that was considered extremely important. The other was 202 Squadron based at Aldergrove. And they were operating Hastings, broadly the same as the MRF aircraft. And they were doing Met reconnaissance, same as FAAM, and they were basically flying out into the Atlantic every day on routes dictated by the Met Office chief forecaster to improve the understanding of the weather systems that were approaching the British Isles. Both those organisations had fatalities, and the work was considered sufficiently important that they simply dusted themselves off and carried on. To be fair, MRF had the odd fatality as well, although their record was a lot better. FAAM and 202, however, have basically vanished into relative obscurity because they were doing reconnaissance. They were not doing the basic science that really pushes things forward, which is not to denigrate the quality of what the people were doing. But both were disbanded. Really interesting thing about FAAM, 1960s, they had a set of pristine, still in service Spitfires. They retired them just at the point where it was decided to form what's now the Battle of Britain Memorial Flight. So those aircraft you have all seen fly at air shows. Some of those Spitfires are still in service. The Hastings didn't fare quite so well. So that takes us up to 2001. Sorry, it takes us up to 78. I inadvertently missed something out. MRF in 78 was about to engage in something called GATE, the Global Atlantic Transport Experiment. The multiple countries, multiple ground observations, multiple aircraft, multiple ships, still the largest airborne experiment that has ever been flown. And matter of national pride and, of course, delivering the science, it was decided that they were going to get a brand new aeroplane to do, or to provide the British contribution to GATE. And the Hercules, which was not long into service, so unusually they got a new jet. One of the new C-1s was taken offline and converted by Marshalls and became this absolutely iconic aircraft, the Hercules W Mark II, which, for obvious reasons, has been known as Snoopy ever since. And Snoopy was a phenomenally capable aeroplane. Huge payload, long range, long endurance, bags of space, lots of equipment put on the outside. The red and white striped nose, of course, is extremely famous. If anyone wonders, that red and white striped nose still exists. It's a centerpiece of the atrium at the Met Office headquarters in Exeter. And in fact, this instrument here, which is called Mars, we're still flying today. One or two scientists have said to me that Snoopy was so successful in generating research papers that despite being an aeroplane, she qualified as a professor in her own right. And she did an enormous amount of work over a very great many years and established MRF as, by a substantial margin, the world's leading airborne research organisation. That was a remarkable time. She did a lot of very good work, as did the team, some of whom I'm still working with. That brings us up to about 2001. 2001, Snoopy was getting old. She was getting extremely expensive to operate. And there was another player. So as established, MRF had basically been a Met Office organisation. Somewhere along the way, Meteorological Office had become Met Office. NERC, the Natural Environment Research Council, had been buying time on the aircraft. NERC, not many people have heard of NERC, despite the fact it was established by Act of Parliament in 1965 and is annually spending 300 million a year of the taxpayers' money today. NERC is the UK's major funder of earth sciences, and you've probably heard of some of NERC's brands: British Geological Survey, British Antarctic Survey, National Oceanography Centre. They're all NERC. NERC wanted more. NERC had been buying about 70 hours a year on the aircraft, but they wanted more. In the meantime, the Met Office were getting a bit fed up of the sheer amount of money they were spending, so they did a deal to create something that got called the Joint Facility, and it was to be 50-50 Met Office and NERC. At the same time, Snoopy was to be retired. She didn't get retired completely, not at that point, although she's now been scrapped. She was bought back by Marshalls and ended up as the test bed for the engine for the Airbus A400M. Although she was finally scrapped about 2 years ago. So this joint facility was created, but on a very different basis. So they went out to tender, and it was won by BAE Systems, British Aerospace as they were then. And it was created as this big, complex mesh of organisations. So rattling around, so the Met Office were 50% owner, NERC were 50% owner. It was to be managed at that time through UMIST, the University of Manchester Institute for Science and Technology. That's now part of Manchester University. BAE Systems were the prime contractor. They were going to operate the aircraft from Woodford. Then they closed Woodford. So ended up briefly at Cambridge, and then our home now at Cranfield, operated for them by Direct Flight, who are now called Airtask, and maintained by Avalon Aero, the one organisation who hasn't changed name or logo in the entire history of the organisation. Sorry for all of that, but everybody likes to get a plug-in, and at least you get the flavour. So we ended up with this aircraft. And this is an aircraft with a lot of history, and it's still making history. Golf Lima Uniform X-Ray Echo, formerly known as Golf Sierra 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 Hotel, was the 146 prototype. So she flew the entire certification program for the 146-100. Then she got stretched, turned into the Dash 300, and flew the entire certification program for the Dash 300. And BAE were then looking for an airframe that they could use to make a bid for the new atmospheric research aircraft contract, and they offered this. So the aircraft they offered was a completely one-off airframe based on this, which has their own type certificate and is designated the Dash 301. And this is what you're looking at. And she's based at Cranfield, flying regularly. Last flew about 3 days ago. And as you can see, is really not a 146 either. I mean, if you look here, you can see external blister here for external instrumentation, lots of stuff on the top, lots of stuff around the nose, external pylons. You can see Mars that used to be on the Hercules is still there. So really, this is a one-off aeroplane that's roughly 146 shaped, all British and doing a really fantastic job of work. So let's look at the aeroplane. Why could we not use a standard 146? Basically, not enough range, not enough ceiling, not a low enough hard deck, and not configured for all the stuff we wanted to put in. So the whole aeroplane between 2001 and 2004 was completely redesigned and rebuilt. We refer to it as the ditching mods. It's a bit of a misnomer. In reality, what we did is they strengthened the hull for high altitude performance. So we can take the aircraft up to 35,000 feet whilst maintaining a normal 8,000 foot cabin. Air conditioning was simplified, basically to make space for all the equipment. And electrically, the aeroplane was transformed out of all recognition. So power systems were put in to feed about 40 kVA into the cabin to run all the instrumentation. You'll be amused to know all of that running through the galley switch. Uprated radar, it's got a Honeywell RDR-4B, pretty much state-of-the-art at the time, still very good. Seemed radical at the time. We put a SkyMap moving map display in. Well, that was advanced in 2001. In practice, that's still there, just because nobody wants to do the paperwork to remove it. But the aircraft is now managed off an electronic flight bag system run on 2 iPads, one clipped either side of the cockpit. We've got dual radals into an enhanced ground proximity warning system. You think you understand EGPWS. Not if you want to maneuver at 50 feet down the English Channel do you understand EGPWS. So we've had to modify the EGPWS to allow us the low-level operation that is essential to what we're doing. And to get the ceiling, we've got bigger engines. So if you know your way around a 146, the LF507-1F FADEC controlled is the engine in the RJ100. We've got that engine, but with the original 146 hydromechanical controls. Our captains who know both types say that's actually probably quite a good thing, as it's not a very good FADEC system. We do also, as you can see there in the cockpit shot, have digital engine instruments. So it's a completely re-engineered aeroplane. But I'm an aeronautical engineer. I love aeroplanes. Most of the people I share an office with couldn't care less about the fact it's an aeroplane. To them, it's a machine that gets their instruments in the right place when they want them. So let's have a think about the instruments. What do we do? If you start top left, you get a feel for our cabin. So we run a racked instrumentation system. So each of those racks will take about 200 pounds of instrumentation. And they're on a standard rack with a standard electronic system. So a university laboratory somewhere or equipment developer or whoever wants to make up stuff to fly, we just send them an empty rack and a handbook, and they make stuff up. And then we've got a very streamlined system that we can bring a new rack in. It's been designed to handbook, and we can probably have that certified to Part 25 and flying in a couple of weeks, which is absolutely essential. If I go round to the bottom, you'll also get the feel. We've got to suck air in, particularly for chemistry and aerosol. So we've got these inlets, mostly up above the top of the cockpit, where we've got relatively clear air. Some of them are de-iced, some of them are not de-iced. De-icing is always a headache for this sort of work. And that brings air in for the chemistry instrumentation up the front. And then further back, we've got control systems for Clyde microphysics instruments. And that's why out in the wings, we've got the 2 pylons. Each pylon can carry 5 of these standard cylinders, which are called PMS canisters. And we've got a whole set of interchangeable instruments, so we can fly the instruments we need for the science experiment we're going to do. What else can we do with it? This is the rear baggage compartment. Round about here is the long-range fuel tank that we fitted, which came out of a BAC 111 of all things. This is a LiDAR, laser radar. What does that do for us? We can pop up to 30,000 feet, fly over layered air, cloud, volcanic ash, whatever, and we can get, using the LiDAR, the granularity, the density of particles, and the motion of air, so long as there's enough particles for us to pick up on, all the way down to the surface. We should be upgrading that in the near future to something that will start to pick out what chemicals are in the air as well. Can't see off this picture, we've also got a system that allows us to drop SOMs, so we can drop instrument packages. At any one time we can have 4, I think, in flight. They take about 8 minutes to fall to the surface, transmit data, temperature, pressure, wind vectors, humidity up to the aeroplane. We can process that in real time, zap it up to the cockpit where the mission scientist has it, and then they can use that to plan where they want to put the aeroplane for the rest of the flight. This we're still developing, but it's an interesting piece of kit. This is called Zeus. It's a static mill, and it measures the build-up of electrical static on the outside of the airframe. Why are we interested in that? Well, in the first place, we just fitted it because the instrument was available and we thought it'd be interesting to see what it said. And it just happened we had it fitted and flying in 2010 when we did a whole bunch of work in association with the volcanic emergency. And a scientist was idly going through the data one evening, and he suddenly said, what happens if I plot volcanic ash density against static build-up on the outside of the airframe? And he got a straight line. So we realized we had accidentally invented an instrument that tells you the density of volcanic ash you're flying through. So we rushed out and patented that just in case anybody else had had the same accident. And ever since, we've been working out how to exploit the technology. If anyone's got any ideas, have a word, we'll see what we can do. So lots of instrumentation. Average flight, about 2.5 tons of instruments. If we're carrying a lot, we can manage about 4 tons of instruments. Together with average crew of about 16 and average endurance of about 5.25 hours plus reserves. So busy jet, doing a lot. Instrumentation, as I said, this aircraft really is all about the instrumentation. So what have we got on board? Well, inevitably, we've got all the primary flight instrumentation, airspeed, true altitude, the radio altimeter, INS, GPS, heading, and we've still got all the prototype strain gauges, and we're still recording them, so I give you strain gauge information from across the airframe as well. That's all there, and we just record it as a matter of course. Temperature, humidity, and turbulence. I was working it out because we're interested in the 3 phases of water. Working it out with a colleague the other day, and I think we came up with slightly over 20 different ways on this aeroplane of measuring water content, and about 5 different ways of measuring temperature. Turbulence, we've got a 5-hole turbulence probe built into the radome in the nose, and we've got something else out on one of the wings. All of that we fly all the time, along with cloud microphysics and basic greenhouse gases. Unsurprising, science is really interested in greenhouse gases. How accurately can we measure? If you need a really fast response, say about 10 hertz, we can give you the main greenhouse gases at an accuracy of about 1 part per million. If you don't mind a slower response, say you can accept 1 data point every 3 minutes, we can give you an accuracy of the main greenhouse gases of about 1 part per trillion. I'm not aware that anybody in the world has a better instrument. We can do a lot of more obscure gases as well. Those top 3 bullet points, we fly all of that all the time. And then, as I say, we call that core instrumentation. And then we've got the non-core, all the specialist stuff of which we've far more than we can fit in the aeroplane at one time. And this gets fitted according to the experiment we want to fly. So are we interested in aerosol, particles suspended in the air? Cloud microphysics. Would you like micron scale photographs of ice crystals as you fly through clouds? I can do that for you. Chemistry. Pretty much any interesting chemicals, we've got a way of measuring it. We might have to suck them into vacuum bottles and put them into a mass spectrometer on the ground, but we can fly mass spectrometers, nephelometers, and so on as well. Remote sensing, we've done a little bit of that, not that much, the odd job for the Ministry of Defence. And I say we've got better turbulence, and as you would expect, we've got a dispersed data system. It's called Decades. We really can't remember what the acronym stands for anymore, so it's just called Decades. It stood for something once. So basically, we have the world's biggest Swiss Army knife. And if you want to deliver an experiment, we'll work with you to determine what instruments you need, who's got them, what scientists you need on board, what scientists you can leave on the ground, where we can operate from, and that is our job. And we're not bad at it. So what's the science we do? It basically falls into 4 flavours. University-led basic research. And the way this works is a university professor writes up a proposal, puts it into NERC or some other funder. They put it through peer review of other professors who have got a deep understanding of the science. They will score it, and then on around twice a year, they line them all up, and the most deserving cases get funded, and they get access to the aircraft. The Met Office, they've got a department in Exeter called OBR, Observation-Based Research, and they exist to improve the forecast, but also to improve the climatology, because the Met Office also owns the Hadley Centre, which is the world's leading climate research unit. So at the moment, university-based research is around 55% of what we do. Met Office work is around 40%, and then the last 5% is in the bottom 2 categories. Emergency, spelling mistake on my slide, my apologies, emergency response. We have a role to serve Britain particularly if something unpleasant is going on in the atmosphere and somebody needs to understand it. We have done the emergency response role 3 times in 14 years. The first time was when the Buncefield storage depot went up. The second time was the Icelandic volcano in 2010. And the third time, which is much less well known, and I'll show you a little about this in a minute, was the uncontrolled release of methane at the Elgin platform 3 years ago. And the last thing is we provide a platform for commercial R&D. If anybody wants to fly experimental instruments, kit, so on, we can do that as well. In particular, we use the external blister for testing future satellite technologies. It's a very good environment for testing, for example, radiometers that will eventually fly on satellites to support weather forecasting or Earth observation, is that you can do a lot of fix, fly, fix relatively cheaply on an aeroplane before you launch something into space. So let's have a look at a couple of examples. So Acacia, aerosol cloud coupling and climate interactions in the Arctic. We are really good at making up long acronyms. It's one of our specialties. This was all about atmospheric processes in the Arctic. This campaign, I went on this, we flew it out of Kiruna in Swedish Lapland. Although these the photograph bottom right is Kiruna. This picture, we are on our way into Longyearbyen in Svalbard, just here. So we'd flown about 2 hours from Kiruna for a refuel and then go off and do work up towards the North Pole. So we developed an aircraft fault on short final, went into hold for 20 minutes and then flew all the way back to Kiruna. We never did make it to the North Pole that trip. But interesting, have a look at this screenshot. This is I took off the cloud physics console. And particular, I mean, you can obviously see the location of the aircraft and a few other bits, but have a look on the right. This is real-time imaging of ice crystals in the cloud we're flying through. Each of those two strips is about 1 millimeter wide. Let's give you an idea of the accuracy we can do that imaging. And of course, that's really important for scientists who need to try and understand the physical processes, because if you know the shape and makeup of the particles in the air, you can try and start to understand what they're doing to the air. Let's have a look at some Met Office work. So this was a great year because this was only 3 months later. So we come back from the Arctic and we went straight out to the Arizona desert. So this was out of Tucson, and solstice, semi-arid land surface temperature, IASI Calval experiment. IASI is a satellite instrument we were also doing some underflight calibrations on. But what were we really interested in here? It was about energy transfer between the surface and the top of what we call the planetary boundary layer, which is around 3,000 feet, over hot desert. Because all of the main weather forecasting models are consistently getting temperatures in the day in hot desert wrong. And they're often wrong by as much as 6 or 8 Celsius. That's a huge error. And of course, forecasters are putting fudge factors in to help, but what they really want is to get the science right in the first place. So we went out there, we did lots of flights at different levels out over the Arizona desert, and then we rattled south down into the Gulf of Mexico. And this was in 2014. So by now, that science is now improving the weather forecast that's going on, that people are getting around the world now. Worthy of mention, forecast models. You've probably all got a rough idea of how a weather forecast model works, but you may not know who owns them. There are about half a dozen really good weather forecast models in the world. The best one, and the biggest one, is called or Unified Model. And it is used by multiple countries around the world. Lots of countries have got scientists and observations feeding into continuous improvement. That is managed by the Met Office, and the core of it is run on the big supercomputer in Exeter. So a lot of our Met Office work is about the and it's about achieving that world best forecast and continuing to try and improve it. Emergency response. So this was a fascinating bit of work. So this was 2012. So on the left here is the Elgin platform. I'm not allowed to call it a leak. Total don't like the word leak. It was an uncontrolled release of methane gas from underneath the Elgin platform. And Total, who operate that field, had an immediate problem because they had to close that. They had to close down several other rigs nearby because of the risk of explosion. And of course, while they were closed down, they were not shipping gas and oil. So they were losing a huge amounts of money. And the first thing they needed to know was how much was coming out. So that's what we did. We did a bunch of very rapid, very good science, and we flew a series of missions downwind, profiling down to 50 feet is the lowest we're allowed to fly over the sea, up to actually only about 6,000 to 8,000 feet because there was no need to go any higher. And we were able to accurately determine, we think our estimates were good to within 6-8%, how much methane was coming out. That allowed Total to design the scheme for capping it off, and then when they'd done that, we went back and we were able to tell them, yes, you have successfully capped that off, and then they were able to rapidly reopen the field. I think we justified our existence. Our bill to Total, I'm not sure I'm allowed to tell you how much it is, but it was under £1 million. And they reckon it allowed them to open that at least a week earlier than they would have done otherwise, and it was losing the company about £20 million a day while it was shut. So we certainly earned our money. So that is the sort of emergency response work we are geared up to do, and we've got a mechanism for working with the Cabinet Office to trigger us and so on and so forth. And then last thing here, we do the odd commercial job. Not as many as I'd like, to be honest, because they're A, interesting, and B, the money's nice. This is probably the single most interesting job we've done over the last couple of years. This was done for GKN. It's an optical ice detector. So it's mounted on the front of one of our PMS canisters, but all that bare metal on the right is GKN's. And the aerofoil section, you can just see in there a little window. That's a laser LED, fires out laser, measures what comes back, and it can quantify the amount of ice buildup. Why does that matter? Well, historically it didn't, because aeroplane like a 747, or in fact R146, has got an ice detector that just says, yes, there's ice, no, there isn't, and then if there is ice, you turn the anti-icing on. Take the next generation of airliners, the most obvious one being the 787. The 787 is electrically de-iced. If you know how much icing you've got, you can control the amount of electrical power that you put into your anti-icing system, and you can maximize that system's efficiency. So this is a bit of technology that I imagine BA will be flying in the next few years. By the way, my first degree is aeronautics and astronautics from Southampton, but I did the specialism there in advanced materials for aerospace engineering. These three components at the front are 3D printed by GKN in titanium and issued with a Form 1. When I was studying aerospace materials, that wasn't even science fiction. So I find that really quite exciting. Just to say, we aren't the only players. We're the biggest players in the UK. I would argue that we're the best in the world, although I have German and American colleagues who might argue with that. This is what the Geosciences research fleet in the UK looks like. So British Antarctic Survey have 4 Twin Otters and a Dash 7. 2 of those Twin Otters are actually parked outside my office at Cranfield at the moment, as they're doing some collaborative work with us. University of Edinburgh have a Super Dimona, somewhat lightweight but with a lot of external instrument capability. Met Office for the moment, not sure how long that will stay in service, have Mocha. It's a Cessna 421 set up as a civil contingency aircraft. And that's got instruments that will handle Buncefield type explosions and volcanic ash and such like. Plus, it's a pressurized aircraft with piston engines that should filter out things like volcanic ash. And at Cranfield, we've got a University Bulldog, which has got a nice little capability for testing instruments, and we use for a bit of cheap fix, fly fix. So that's sort of the scale of the British fleet, and inevitably other countries, particularly in Europe, the Germans and the French have capability. Spanish are just commissioning a new aircraft, and the Americans have got several fleets of quite interesting aeroplanes, mostly at NCAS in Boulder, Colorado, or NASA Armstrong in California. That's where we are. Where are we going? Current aeroplane, if you want my best guess, I think we'll be retiring her around about 2029. We've been doing quite a lot of study work over the last couple of years about what to replace her with, because it's likely to be about a 7-year project to replace the aircraft once we press go. My best guess is that we'll replace her with a high-end business jet, something like a G650 or a Falcon 8X. I particularly like the Falcon because the third engine gives you a lot of scope for operating over the Antarctic and middle of the Atlantic and so But we're still going to go with the Swiss Army knife approach. Going for a smaller aeroplane will give us problems. We're going to have to miniaturize a lot of the kit, but we're doing that already. Our biggest technological problem is most likely going to be cooling. Because even with miniaturization, it's probably going to be generating a lot more heat than a current business jet air conditioning system will handle. The cheap fix, fly, fix, the Bulldog is quite handy. We've been testing some basic methane instruments and so on in it lately. The CAA's conditions that came in a couple of years ago, that's in CAP 1220, that allows chartered engineers to directly oversee, without external oversight, flight testing an aircraft up to 2 tons. That's something we're taking an active interest in, and I think in the next couple of years we're going to be using that on various aeroplanes for equipment testing. And also for both the 146 and going forward for whatever replaces her, I think we will be broadening our capability. So I go around universities doing seminars about how we could use this aeroplane for aeronautics research. We've done things like the GK and R&D, and we routinely talking to people who are developing satellite instruments about using it as a platform. And there are certainly other countries who want a slice of this pie but can't afford their own aircraft, so who are talking to us regularly about whether they can make use of our aeroplane to do their science. And we do things like run European Union-funded summer schools for PhD students and that sort of thing. Invariably, when I give a talk like this, somebody will ask me in the question and answer, why don't you just use drones? So I'm just answering the question now. Why don't we use drones? Well, we do use drones. This is NASA's Global Hawk, and we've done work collaboratively with that out of Guam in the Pacific. But it's best to understand where things really sit with a drone. Are they cheaper to run than a manned aircraft? No. Put in perspective, our 146 operating out of Guam, we were flying typically 3 tons of instruments, so that would be 30, 40 different instruments, and it would tie up for the duration of the flight probably 20 people. Crew of about 16 and 4-ish on the ground. NASA could fly 500 kilos, about 10 to 15 instruments, and that would tie up 25 people. And we delivered every single flight scheduled, and they delivered about 1 in 3, because that aircraft is so limited on conditions. So it is not cheaper, and it is not more reliable. And also, if I've got a dozen scientists in the back of the aeroplane nursemaiding their instruments, our data quality is fantastic. Whereas if you've got to automate something for an entire mission, there is a limit to what you can do in flight calibration, fixing problems that emerge and so on. So data quality is not necessarily as good for a drone as it is for a manned aircraft. Plus, I can fly bigger instruments, and if it's bigger, I can make it better. But drones can do stuff, and the community refer to the 3 Ds. If a task is dull, dirty, or dangerous, use a drone. So if I want to fly taking measurements inside a volcanic caldera, I am not putting a manned aircraft in there. NASA's Global Hawk was giving us 36-hour missions at 70,000 feet. I'm not going to do that with a manned aircraft. That aircraft doesn't exist. So drones have a role. They are a part of the future. They are allowing us to do science we could never do before. I don't think they are about to replace the manned aircraft for the work we're doing. The other thing to mention, a lot of people love the idea of buying off-the-shelf cheap instruments and flying them on low-cost, lightweight drones. So, here is an experiment. This is a real photograph from a press release from a scientific project. Some bright spark caught a load of London pigeons, fitted them with temperature sensors that downloaded on Wi-Fi, and released them. And the idea was they would fly around London, developing data of the London heat island. Whenever they passed a suitable antenna, it would download the data, and they would get this fantastic data set. Now, I don't know if you've ever watched pigeons. They huddle up at night on a little ledge. They get caught in the rain. They fly through whatever muck is around there. Do you really believe that after it's been strapped to a pigeon for a few days or a few weeks or a few months, that that instrument is worth anything in terms of data quality? Because I don't. And this is another thing. We need to maintain the quality. And actually, if we're using a drone, I also need to really well understand the flight characteristics of the drone, the flow field around it, the thermal signature, because I need to use all of that to inform the calibrations of my instrumentation to get the best quality data. And again, you're not going to do that with a 500 quid drone that you bought from Maplins, and you're not going to do that with a pigeon. Other issues that you've got tends to be that universities give some PhD student, young postdoc, these projects. Their job is being a scientist. They're probably very good at being a scientist. That doesn't make them an expert drone operator. So where's our expert drone operator? Are we going to have a good scientist who's an inexpert drone operator, or are we going to have an expert drone operator who knows nothing about science? We need the teams. And the other thing with drones, compared to manned aircraft, our 146 has got a full ICAO-compliant C of A. I can fly that within limits anywhere in the world, and the paperwork is pretty straightforward to get permission. Drone systems have no equivalent international standard. So if I want to take a drone system that we've managed to get permission out of the CAA to operate here, and we've been doing good science up in the Cairngorms or something, and then take it to America, I am starting completely from scratch with the FAA because their systems are different. And then I'll take it down to Mexico and we'll start again. So drones, they've got a lot of value, but they're not going to replace manned research airplanes. And that was my talk, which I hope you found interesting. Do take the postcards away. There's a load of leaflets here about stuff we do. Feel free to take those as well. And I'll take as many questions as I can until they throw us all out. Sir?
You do so many, such a wide range of jobs, but I just wondered how much is commercial and how much is MOD?
How much, the question is, for what we do, how much is commercial and how much is MOD?
For example, is that considered MOD?
Is what considered MOD?
Met Office.
Right. Met Office used to be a defence agency. It's now part of BAES, Department of Business, Energy, Innovation, and something or other. So in fact, they take their money from the same place as NERC now. We take a little bit of MOD money because they like having our capability there to test a few things. We probably, if I was to put a figure on it, I don't have the figures on the top of my head, I would say less than 5% of our work is defence and probably 2-3% is commercial. The bulk of what we do is public funded science. I say I'd be really happy to do more commercial, but we're a very expensive tool and nobody's going to use us if there's a cheaper alternative, to be honest.
The BBC now giving you, well, on the internet, giving you weather forecasts for 15 days.
Yes, and it's rubbish. Okay, this is not my talk, but I know the answer anyway. Historically, the BBC bought their weather data from the Met Office. They switched a couple of years ago on competitive tender to a company called Meteor Group. There were significant teething troubles, but early this year they switched properly. So Meteor Group is now providing the BBC forecast. That's fine. Actually, Meteor Group have got some good forecasters. They've got access to good models. They're reasonably competent. NCAS, National Centre for Atmospheric Science, who are one of our parent organisations, actually also have the contract from the BBC to monitor the quality of Meteor Group's forecasting. So I've got foot in both camps. That's all fine. Now, what's not fine, in my opinion, and certainly in the opinion of most of the professional meteorologists I know, is that the BBC is now issuing a forecast down to 15 days with a resolution of 2 hours. That is patently nonsense. The science just doesn't support it. You can generate quite an accurate forecast most of the time up to about 3 days. About days 4 and 5, you can develop a pretty good forecast to a resolution of about half a day. You can probably say on day 5, it's quite likely that it'll rain in the morning and it'll be sunny in the afternoon and the temperatures will be about this range, is about how good you can do it. By the time you get to day 7, you're into climatology. Basically, by day 7 and certainly day 15, all you can realistically say is it will do about this because that's what it usually does in mid-April. So the BBC's long-term weather forecast, every meteorologist I have spoken to says this 2-hour resolution 2 weeks ahead is just a nonsense. But certainly 3 to 5 days, Meteor Group's forecast appears, from what I understand, to be pretty good.
Turning to the emergency response, how quickly do you have to be airborne?
How quickly do we have to be airborne for emergency response? That's a good question. Our role is not to be a first responder. The first responder is MOCA, the Cessna 421. And if they get a call from the Cabinet Office, they have to be airborne they have to be airborne where required, anywhere in the British Isles within 24 hours of being triggered. In practice, I think they can be a lot faster than that, but that's what they're contracted to achieve. We're different. We have the capability, and we will be, the Cabinet Office or whoever will contact MOCA first. MOCA will talk to us fairly quickly, and we will monitor what they are doing, and we will identify whether we can do something useful, and if so, what. And what we will then do is we will go to the relevant agency and say, if you want us, here is our present capability. We can deliver this aircraft, this instrument capability, in this location, and by the way, it'll cost you that. And then it's basically up to that government agency to decide whether they want to use us. Elgin was a good example. I mean, we were in a really good place because it just happened. The aircraft had just come back from a campaign in the Arctic the day before that happened, and we'd been measuring methane over the Arctic, so we already had all the right instruments on board. And so we went to the Cabinet Office and said, capability, sat here, do you want us to do anything? And by the way, it will cost you this much. Cabinet Office scratched their head for a couple of hours, came back to us and said, nah, not our problem, talk to Total. We then went and talked to Total, who were extremely enthusiastic, and they said, yep, we'll have you up in the North Sea as soon as you can get there. Can we please put somebody on board the aircraft, although in the end they never did. They worked really well with our scientists, and we delivered what they wanted. So that was the way it worked there. But there is not a right answer. Because we're not set up as a first responder. So, for example, the aircraft has just come back from Alaska. Clearly, when we were operating out of Fairbanks, configured out to do atmospheric physics up towards the pole, Doesn't matter what went wrong in British airspace, we weren't going to be there that week. But that's why MOCA exists. So.
As a generality, what you seem to be saying is that you normally understand the processes that are taking place and the materials that you're finding. You may have a certain number of combinations of materials that you need to, that are new to you and so on and so forth. But the main challenge seems to be picking up the information in this particular spot that you can then feed into computers and make projections from that.
There's two aspects to getting information into a forecast model. One is the direct observations of temperature, pressure, humidity, wind, cloud, pollution, and an aeroplane nowadays is a really expensive and inefficient way to do that. We do a little bit of it, but really only because we can. When we're out flying a science campaign, a proportion of our data gets fed into the Met Office supercomputer simply because we can. And it just adds to the quality. That's not what we do. That is all being done by instruments on ships, by satellites, by ground observations, by Stevenson boxes on airfields, thousands and thousands of data points. What we are doing is understanding the physical processes that allow the improvement of the model. The model is what then uses this data to create the forecast. So we get tasked to go into the places where the science says we don't understand the science well enough. So like energy transfer over hot desert, like the behavior of low pressure regions in the Arctic, like the emission of greenhouse gases from palm oil plantations in Indonesia, which we've gone and done. And us doing that this month is not going to have any impact on the quality of the weather forecast this month or next month or quite possibly next year. But what it is doing is allowing the hundreds of scientists who manage the unified model or similar models to improve the processes as they exist in the computer models so that after a couple of years, once this has been properly understood and used, you can produce better forecasts.
Can I ask a follow-up question?
Go on.
Because we've got the European Centre for Medium-Range Weather Forecasting based in Reading. It's been there for some time.
Yeah.
I mean, I've got no awareness of how relevant that facility is or is not anymore. I mean, are they able to keep it relevant by just upgrading the software or what?
ECMWF run their own models. ECMWF are running their own models. So they've got a slightly different slant on it to the Met Office. The Met Office tends to be much more focused on the now to 3 day forecast. ECMWF tend to be rather better on the 3 to 7 day time scale. But actually, a good forecaster, or even, frankly, a talented amateur like me, who knows where to look, will be looking at might be looking at the NOAA model, will be looking at the ECMWF model, and looking at the outputs from all of them and comparing them and forming an opinion about the range of conditions that may occur. And this is another thing that's worthy of mention. If you compare a general public weather forecast from the BBC, they will basically say, tomorrow afternoon it will do this. On the other hand, if you look at the Heathrow TAF, it will say tomorrow afternoon there is a 30% probability of this, a 50% probability of that. That might happen for up to half the time. The first is deterministic forecasting. The second is probabilistic forecasting. I think, to be honest, probabilistic forecasting is far more honest. And I understand there is a move to start trying to move the public weather forecasts more in that direction. And certainly aviation forecasts are already there. And actually, if you look at a public weather forecast in North America, they're already probabilistic. So we're perhaps a little behind the times in the way, not we do the science in Britain, but in the way we present a weather forecast to the public.
It's very interesting. Thank you.
Gentleman here.
Yes, you mentioned the volcano in Iceland.
Yeah.
We were all grounded for about 10 days. Did you get involved in any flying?
Yes. In fact, I was mission scientist on the first 2 days' flights into the ash cloud. It was a very strange experience. We got caught on the hop somewhat, as the two obvious aircraft to put up into it, the 146, and at the time we also had a Dornier 228, were both on the ground for maintenance. We realized halfway through the first day that we couldn't just sit and look and wonder what was going on. So we took the decision, we put some of the 146 instruments onto the Dornier and we flew into that. So it was the 14th of April, the airspace closed. And we pressed go at about 11 o'clock that morning. And we had the Dornier up, as I was mission scientist on board, at about 7 o'clock that evening. And we flew up to the middle of Scotland and back and overnighted from Cranfield and overnighted at Brize Norton. And we didn't see anything at all. We will never know whether that was because there was nothing where we flew or we simply hadn't got the instruments in a good enough state. Second day, we flew again, and we'd done a lot of overnight instrument work, and we found a lot of ash. And we then, working with the CAA, we activated the 146 a couple of days later, flew the 146 and the Dornier together for a couple of days, and then realized we didn't need the Dornier, moved all the instruments and scientists over onto the 146 and did everything with that. So, yeah, we were very active. We had an aircraft up the same day. We had 2 aircraft up by day 5. Shortly afterwards, another European country actually got an aeroplane up into it. So Britain was massively leading the field. And we did a great deal we weren't the only people in the game at all. In particular, I would say the man who really, really made a difference was the head of airworthiness at the CAA, a chap called Porrick Kelleher. And they gave him a medal for this later, and he thoroughly earned it. So with Porrick's leadership, us actively participating, whole bunch of other players, Rolls-Royce and General Electric basically pooled all their resources to solve the problem of what you could actually fly a jet engine in, because nobody had really asked the question in that way before. And we got everything unfrozen, I think, as fast as humanly possible. I should say, we did substantial damage to the engines of the Dornier, but probably not caused by volcanic ash. Interesting thing we realized in retrospect, the volcano had been erupting through a glacier. So a huge amount of water had been melting into the caldera, and you pour all that water into all that molten sulfur, and you get a fairly nasty mix of acids. And we certainly measured aspects of that. I mean, we weren't geared up for chemicals of that nature, but we had enough instrumentation to see roughly what we were in. Is the whole UK for several days was starting around 1,500 feet, covered in an aerosol of a fairly nasty mixture of sulfur-based acids. And yeah, we ended up having to replace both engines on the Dornier. And I think had airline operations continued, in retrospect, we probably wouldn't have suffered an awful lot of ash damage, but you would have suffered enormous, many millions of pounds of maintenance problems as a result of all the acid. So, yeah, we closed the airspace at the right time, and we were right to close the airspace, but we may have actually done it for the wrong reasons.
You mentioned you were an enthusiastic meteorologist. I'm a pilot, so I do have a little bit of interest in meteorology. A gentleman mentioned the Reading Centre. There's also GFS and the Met Office. How, because I obviously look at all of them, if I can. I've never heard of UW. Could you mention a bit more about UW and whether it's publicly available?
Unified Model, that's the Met Office. Unified Model is the Met Office. A lot of the free sources you see are GFS, which is the American NOAA data source. And there are some sources from which you can also get ECMWF data. Those, I would say, are the three main ones. There's a whole bunch of tools. I'm a pilot as well. I've got a couple of thousand hours, and I fly the Bulldog, amongst other things. I particularly like one, this is just my preference, called Windy. And the reason I like that is it allows me to pick up the area, pick up the timescale I'm interested in, and then I can flick between the models and look at the outputs of the multiple models. And my take on this would be, given the models work in slightly different ways and using some different assumptions and so on, if all three models are saying about the same thing, you can probably trust the forecast. If, on the other hand, I've got different models saying significantly different things, what that's really telling me is there's a lot of uncertainty because we don't entirely understand where it's going in various directions. And that's the point where I would tend to be very cautious and probably, as a matter of course, hope for the best but plan for the worst in terms of the weather outcomes. But yeah, there's a whole bunch of stuff there, and it is difficult, I agree, to know exactly where everybody is getting their weather feeds from. And of course, as pilots, our preference is the provider that seems to give us the clearest and most readable information. And that's actually a bit of a headache because I'm not going to name anybody, but I can think of at least one provider who provide really high quality forecast and then present it really badly. But it's worth pursuing to improve your understanding of what's actually going to happen. On the other hand, there are a few who are taking the American GFS data, and GFS, it's quite good for Europe, but it's not as good as, say, the UM, because the UM is optimized for the British Isles. So they're taking data that's probably not quite as trustworthy for the British Isles, but then presenting it really, really well. Therefore, people are tending to use it because they like the presentation. So it's a difficult thing, and unfortunately, there isn't a really good, simple answer I can give you. So.
I'm surprised you don't really miss not having anything above 35,000 feet.
We do.
I'm surprised you would say there's some, okay, unmanned instrumentation, but why don't we have flying drones and things like that?
Well, we've bought time on NASA's Global Hawk for operations out in the Pacific, and that allowed us to do a bunch.
Would you rather have them flying above you?
Well, that's what we did. The campaign, it was called CAST, that we did out in the Pacific. We had 3 aircraft. We took the 146 and we were doing the low level. NCAS brought a Gulfstream 4, I think it was, and they were basically doing everything between about 20 and 40,000 feet. And then NASA brought the Global Hawk, and they were doing everything around 60, 70,000 feet. So between the 3 aircraft, we were able to get a really good vertical picture. And we've done variations on that in other parts of the world as well. Has British science got a problem with the lack of stratospheric capability? Yes. And in fact, I'll go further. I say European science. I go to a couple of meetings a year at a European level looking into how can we improve European stratospheric science capability, because every major science country in Europe recognises that we have an emission. What are the solutions at the moment? Well, DLR's major research aircraft, which is called Halo, is a G550. That can go up to 45-ish thousand feet. So that helps, and that will at least get into the temperate, lower stratosphere. There's a Russian aircraft, an M55, which is converted for science, called the Geophysica, which is variably available but is used by various science campaigns around the world, and that can get you up to about 65,000 feet. NASA operate 2 aircraft, an ER2, which is basically a U2 converted for science. They've got 2 of those. And believe it or not, 2 WB-57s, otherwise known as Canberras. And NASA are still operating Canberras, which is a British aeroplane. We are really interested in getting our own Canberra, and we have had meetings. There are 2 potentially airworthy Canberras in the UK. WH-134, which is at Kemble, which was on the display circuit until a couple of years ago, which is a PR9, and WK-163, which has been just acquired by the Vulcan to the Skies Trust and is at Doncaster. And I've been having meetings with both of them about the possibility of flying one or other of those Canberras for atmospheric science. We haven't found a way to do it yet, but we are continuing to look hard at it because it would add value. The biggest reason it would add value actually is not weather forecasting, it's climatology. Because a lot of the science of understanding climate change is about transfer of chemistry across the tropopause. And therefore, if you are going to understand that chemistry, you need to put an aeroplane with quite a lot of complex chemistry instrumentation capable of flying across the tropopause multiple times. We can do this in the 146 out of Prestwick in November, but that's going to tell us nothing about what's going on over the tropics. And if we're going to go to the tropics, I mean, that's why we were using the Global Hawk, and that's why we would like to be able to use something like a Canberra. And we're continuing to look into that. At the same time, NASA, who have got their own funding problems, are really very keen to sell us time, particularly on the ER2s. So the capability exists, but domestic capability in the Britain at the moment, no, it's a big hole. Looks like we might be finished. Did you have a... do we have a liaison with the French? Yes. The French operate an organisation called Saphir at an airfield just outside Toulouse. They operate 3 aeroplanes, an ATR-42, a PA-34 and a Falcon 20. They are in the process of retiring both the ATR and the Falcon, probably replacing them with something like a Falcon 2000. We visit each other, we borrow good ideas off each other, we've flown into comparison flights occasionally, and we've certainly had a chat about when they retire the ATR about whether we can plug some gaps in their capability. Plus, we might be able to do something with a Falcon as well.
From across the globe, from the centre of aerospace, and now to you.
Thank you for downloading from the Royal Aeronautical Society. If you enjoyed this content, please consider showing your support for the Society. Share a link to this presentation by email or on your favourite social networks. If you have an interest in aerospace, consider the professional and personal benefits of membership. Visit www.aerosociety.com.